Good afternoon, everybody. My name is Jimmy Moore. You are now in session for Best Paper number 2. This is our second of 2 sessions with the best papers voted for by each one of the session committees. Give yourself a hand. You've made it halfway through ITSEC. Nice job. As I said, my name is Jimmy Moore. I'm the chairman for the simulation subcommittee. I'll be chairing this session with my partner, Mark Covey, who was my deputy chair this year for the simulation subcommittee. We thank you for attending this paper session this afternoon. I just have a couple of announcements before we get started. This session will be recorded, so please remain in your seats through the duration if you wouldn't mind. We will have breaks in between each one of the sessions so that you can rotate out if you need to get somewhere else. Each paper will have 20 minutes for the presentation, followed by a 5-minute Q&A. So please hold your questions till the end of the presentation. We'll stop exactly 25 minutes after so that we can give you guys a chance to rotate out if you need to and give the next presenter a chance to get ready and get set up. If you do need to leave before the presentation is over, please be aware there's a camera right there and the exits, use the exits in the back if you don't mind. And then as a reminder, all conference registrants are eligible to obtain CEU credits for all paper presentations this year. So if you need to do that, please see myself or one of the folks with the orange badges on there with operations. So our first paper is out of our ITSEC committee. That's the Emerging Concepts Committee. It's Optimizing Optimizations, a 2-stage neural network approach for leveraging optimally in-time sensitive solutions. Our author is Matthew McLaughlin. He is lead computer scientist at the Fires Battle Lab in Fort Sill, Oklahoma. He has a BA in mathematics and a BS in computer science from Cameron University. He also has a master's in engineering in modeling and simulation from Arizona State University. Matthew?
Okay, so this research started as a side quest to some research I did a couple of years ago. I then used that research as the use case for this paper presentation. I had mathematically worked out an optimization problem as much as I could by hand and brought it into a computer. I imported a library called GSL to handle the actual optimization. I just give it an output for whatever input it gives me. But it's not that simple. In order for it to run, I had other variables I had to fill out. These included the type of convergence algorithm, step size, stop threshold, and several other factors pertaining to solving optimization. My background in math tells me what some of them might mean, but really I don't know their effect or interactions on the solution. I played with these variables and observed that some runs were fast and terrible, some were slow but near optimal, some were in between, and some runs were slow but also not good. If anyone out there has toyed with processor-intense computation like training neural networks, what decisions did you make when you selected its depth, its layer sizes, its activation function, its thresholds, or flavors of backpropagation? Or did you just follow an online tutorial and trust the defaults? Now take away all the fun and curiosity and put the pressure of deadlines on producing a high-quality model. Speed of relevance. I found this phrase in the National Defense Strategy during my literature review, and I think my research lines right up with this strategic concern. This bit of code demonstrates a solution to a time-sensitive problem. If someone calls this function, they anticipate its return to be a data structure containing tomorrow's date. Ideally, computation should be instantaneous, but the reality is that processing time is a side effect of computation. This programmer decided that the combination of waiting 24 hours inside this function followed by retrieving the current date is sufficient. The solution is correct relative to the time the function is called, but incorrect relative to the time it finished. A better algorithm could be just as accurate, but take much less time. Time-sensitive problems exist everywhere. This was a silly example, but it demonstrates the degradation of usefulness as time passes. My use case focuses on maximizing the damage on a target area, but my aimpoint solution degrades because enemy targets move. Other examples of time-sensitive problems include a wide range of applications like forecasting, optimized short-term planning in logistics and manufacturing. All of these solutions degrade to the point of being unusable. Depending on the problem set, a good enough solution now is better than doing nothing but wait for that optimal solution later because it's no longer relevant. So meta-optimization is the technical term for optimizing optimizations. It just sounds less catchy. Algorithms are essential to problem solving, but they increase the complexity of the software and add parameters that are meaningless to the end user. The actual algorithms and parameters depend on the type of problem being solved. Optimizations problems typically have a choice of convergence algorithms, step size, stop count, or stop threshold, number of repetitions. Meta-optimization attempts to optimize these algorithms for speed. They are important because they assign values to these artifacts, making them less susceptible to human misconception. But this makes meta-optimization rigid because the end user now has no control. Tunable meta-optimization addresses the phrase speed of relevance by allowing the user to pass in a desired deadline. Now, instead of a bunch of knobs that are meaningless to the end user, they have one knob for what matters most. This diagram shows where the meta-optimizer fits in. We have the problem being solved shown as inputs coming in from the left. Our tuning knob comes in on the bottom left. Based off the problem set, we could leverage other resources, not just time, by adding more tuning parameters. The meta-optimizer takes all of that and produces an optimal control configuration shown connecting these two blocks. These lines are the hidden knobs required to solve the problem. If a human were to fill the role of the meta-optimizer and be trained, they would first tinker with the software. Every request would realize processing time and have random noise. Is that an effective way to learn? We will quickly find that we jumped ahead of ourselves. We can't train a meta-optimizer efficiently if we don't even understand the software it optimizes. So forget the meta-optimizer. We'll come back to it in a later stage. We first need to create a model that predicts processing time without making us wait. We take that processing time, compare it to the user-provided deadline, and add in a metric of solution quality to obtain the score. This score melds together multiple objectives as shown below. Note, it is not the only way to write a score function. Mine might be a little too simplistic, but it provides an objective way to minimize processing time and maximize optimality. We begin with a designed experiment, run the real software, and record processing time, resource requirements, optimality, and so on. Open up this table in Excel, add in a column and levels for tuning, and calculate the score. Now employ supervised learning to train the cost model to produce a score for any configuration of inputs, which come from the user, controls, those required but annoying variables we are hiding, and tuning parameters. With a fully trained cost model, we can quickly evaluate the meta-optimizer. The cost model replaces the actual software, and the meta-optimizer network can now be trained more rapidly and without randomness. I use reinforcement learning on the meta-optimizer so that it is better trained for its operational use. The meta-optimizer is considered trained when the overall score is minimized. Swap the cost model back out with the real software and we're ready to go. While I have this slide up, my boss came to me a couple of weeks ago and asked if this research could help commanders make decisions on how to carry out their missions. After a few minutes of doubt, I realized, why not? The mission comes in as inputs, things the commander cannot control. Let's say it's a survivability move to a location. The control factors are what the commander can control, like routes and behaviors. The tuning variables are what the commander would rather control, like risk. After all, the routes he or she selects is usually based on risk to life and timeliness anyways. In this scenario, we don't meta-optimize around software to run faster. We meta-optimize around simulation to achieve the mission, shifting from a time management perspective to a risk management perspective. But that's all a future paper. Optimality is a topic that is very relevant to my use case, but not relevant in all use cases, as I'll mention later. I want to maximize damage on a target. If I run with a bunch of repetitions over a long time and keep updating the best solution as I go, this best solution so far will approach a maximum, as shown by this graph. Here, I may only ever hope to achieve 70% damage. Optimality measures the degree of closeness to a global solution. I went with a common 9-count definition, which literally counts the nines, in the leading nines in a decimal number. For example, 90% is 19, 99% is 29, 99.9% is 39, and so on. But how do we count the nines if the global maximum itself is unknown? It's generally impossible. Generally because some solution sets are finite and found with brute force algorithms like the well-known shortest route traveling salesman problem, or perhaps the global solution can be calculated or proven. For most other applications, we're on our own. Remember the training data? Remember the experiment data that trained the cost model? If we haven't thrown it away, we can look at its training data. Remember, the objective function depends on input variables, not control variables. If we select the best return value for each input configuration, irrespective of the control configuration, we have a solution potentially near the global solution. These maximums go into a database. We can repeat runs or focus on high quality runs to improve the quality of the approximated global maximums. These are some notes I should mention. This is all performed in the software release pipeline. The Meta Optimizer is updated in the software before it is released to the users so they can start running their time-sensitive problems right away. Software is bound to change. Training in the pipeline will capture those changes and start taking advantage of them before the software is released. Say that a new heuristic algorithm was added to the code. The Meta Optimizer training could inform the software manager that it performs well and will be selected in certain situations, or that it was never selected and could be excluded from the release altogether. I also mentioned in the paper which software changes should invalidate the global maximums database based on whether the code change is inside or outside the objective function. As I mentioned before, my use case is all about selecting optimal artillery aim point locations to spread effects on a target area and maximize damage. The target area could be geometric or be made up of one or more target reports. I show a cluster of targets on the right and one really inaccurate but high priority target on the bottom. I like this use case because it's very visual, easy to understand without an artillery background, and most important, it is a time-sensitive problem because the enemies move. The optimal solution delivered too late is useless. If I spread out aim points too far, I'll spill effects outside the target as shown by the top picture. All that red and yellow outside the target area has no impact on the overall mission. But if I shoot my rounds too close to each other, my effects will overlap. The bottom picture shows overlap and lots of white areas in the target. The right amount of spread is what makes this an optimization problem. This was the research I did before. It had a lot of math, as we can see here. I converted damage patterns, round impact air, and target area into mathematical models. simplified them by hand, and converted these formulas into common image processing routines like layer combination operators and Gaussian blurs. This software implementation approach made it run faster than I expected, so I got excited and wrote a paper about it. Here are some sample solutions from that presentation. I demonstrate all types of shapes and damage patterns. The dinosaur shows how extreme target complexity is not a challenge for this algorithm. I won't go into too much detail on the next few slides. My use case is really just an example of tunable meta-optimization. I created 6 target shapes. I extracted some measurements from these scenarios to describe the target shape and complexity in a few parameters. Since the scenario itself is a blocking factor, I also have inputs on the size and shape of the damage pattern relative to the target area. The number of aim points, the round impact error is also given as an input. These factors all describe the problem being solved. They all have some meaning to the end user. When the software accepts this user request, some analysis is performed to generate these inputs. Control factors don't really have much meaning to the end user. They describe how the problem can be solved. In here, I have a convergence algorithm. The resolution describes the number of points sampled for damage across the target area. Stop threshold tells the optimizer to stop if it's only making small adjustments. Step size describes the scale of aim point adjustments on the first step. Repetitions run in separate threads because they all start with their own independent sampling of aim points across the target area. And some genetic algorithm parameters are also thrown in. On the right, I have my output, processing time, optimality, and the combined score, as I mentioned before. I ran the design. Here, I decided to show a quick ANOVA for just the main effects on the score. The R squared shows around 80% of the total variance is explained by the main effects. The neural network brings a 71% reduction in the remaining error sum of squares from the last slide. The meta-optimizer was then trained to reduce the output of the cost model, as I mentioned before. I give the network architecture, layers, dimensions, and activations as shown. To my surprise, some of the convergence algorithms had no real strengths. This graph shows the mean selected control value based on the range of that parameter, low and high. The trained meta-optimizer selected only 2 algorithms and trades off between them, BGFS for speed and Simplex 2 for quality. A bigger surprise to me was the number of reps never changed. These reps ran in a multi-threaded environment, so I don't know the effect parallelization really had, but it was apparently more advantageous to just control the speed of the rep. I wanted to go back and mention some applications before I conclude. I showed an optimization application, but there are many others that I have yet to explore. Functional equivalence meta-optimization is a problem set where all solutions generate the same output, but the output is generated differently. These are used a lot in programming. It is the choice of programming language, data structures, algorithms, software design and architecture, and compiler optimizations, all of which produce software that performs the same task, like getting tomorrow's date. I mentioned neural networks as something that seems to have a lot of configurations that all seem arbitrary. Feed forward is a simple architecture, but it still has depth, layer sizes, layer activations, and so on. Lots of research exists on using some patterns, but how do we infer those patterns' range of usefulness? And in general, any software system that exposes algorithm parameters or optimization parameters can be tuned. Future work. I would love to explore other use cases, but this one was an easy choice because I wrote the code and could easily change an interface with it. Even though aim points do not relate to a large audience, it's very visual, easy to explain, and I underline the generality of this research. After finishing this research and submitting it to ITSEC, I continued to tinker around with the process and got better results and more insights. I feel like this research is very young, but has the real potential to expand into vast areas of research opportunity. The top bullet attempts to write a score to punish the squared deviation below the expected maximum. The score function I used earlier was linear, allowing good and bad scores to just simply cancel out overall. The process I discussed so far was pretty straightforward and definitely lacked good analytic evaluation. This is in part due to the page constraint, but it breaks the scope of this introductory research, which frankly needs years of additional research to really optimize optimizations optimally. I expected a bigger eye roll from the audience. To sum everything up, the goal of my research is to speed up software in a well-informed way. In the first stage, I used supervised learning to train a cost model to take the place of the actual problem-solving software. It is model-based, deterministic, and computes a score to quickly evaluate meta-optimizers. In the second stage, I used reinforcement learning to train meta-optimizers to reduce the overall score. The trained meta-optimizer is packaged up with the software release. The meta-optimizer hides parameters so that humans do not unknowingly run software in slow and non-optimal ways. Retraining the meta-optimizer in the software release pipeline allows it to adapt to software changes. Tunable meta-optimization allows the operator to obtain solutions fast or better solutions later, a critical feature for managing solution quality and deadlines. Any questions?
On one of the earlier slides, you had a dial and had fast on the left and had quality on the right. You had somewhere up there useful. So I would take it useful would be somewhere on that dial. Couldn't you just leave the tuner lined up with useful?
Good question. So I don't really anticipate the end user should be burdened necessarily with the tuning of that knob, but you have to be able to quantify the degradation of the solution, such as if the enemy is moving or not. You find the intersection of local solutions with the degraded maximum, and you can usually use that to pass in an optimal deadline. Now, that's sort of the weakness of that aim point algorithm. It's timeless. It works best if your detections are processed, a solution is also processed, and rounds hit that target all at time 0, or the enemy's just hasn't moved. And I mentioned before that you could add additional tuning parameters, but you could also have no tuning parameters. And that would be if you took into account that degradation. I could have run all of this in an army simulation and optimized on the number of targets destroyed rather than scattering sample points around the target area. That way, degradation is accounted for in the output of the simulation. Good question.
We have time for one more.
I get the impression computation was fairly cheap, but you mentioned using a design of experiments. Not just possible to randomize and cover the whole possible solution space.
Yeah, so there are some pros and cons to using DOE as opposed to just randomly assigning it. So the obvious answer is DOE reduces the confidence interval on parameter estimation. It's also easier to generate an analysis of variance. If there's a lot of factors I want to screen, I could see if any of those inputs or input or control factors have any effect on the output, and I can throw them out. But more specifically, I measure optimality. So I had to keep the number of unique input configurations low, since the global solution is based on input configuration irrespective of the control configuration. And I had to start somewhere. I could randomize all the inputs, as you mentioned, but and the neural network would definitely handle the curvature of the model better than a bunch of a handful of discrete levels in DOE. I have yet to build tools for good analytic evaluation to explore best practices.
All right, let's give Mr. Rabab a minute. We will have a 5-minute break and we'll head for the next paper. Thank you. Man, awesome.
Thank you.
Terrific. I understand a word. It was terrific.
Oh, really?
No, it was great. I'm just kidding with you. My wife's a math major. I get her all the time about all the stuff she comes home with.
Well, that part that my boss, when he came in and asked that question, I had a little bit of doubt. I thought that would relate a little more to this audience. Almost made me want to pull my paper